All right, I think we are all set up. Welcome back, everybody, to Ask a Scientist. This is the end of our space week. So thank you, everyone who has participated in our summer camp boxes and followed along with our daily dose of science activities. We're going to round it off today with a really cool talk about mapping our galaxy. Today, I have Dr. William Armentrout with me, and he's an assistant scientist at the Green Bank Observatory, which is a really amazing telescope, the largest on the East Coast, I believe. And so he's going to be telling us all about kind of what a day at work looks like for him, and I'm really excited. So make sure you send in your questions to Facebook, and I'll make sure Will gets a hold of them and gets everyone's questions answered. So you can just take it away, Will.
Thank you very much for that introduction. As Abby said, my name is Will. I live deep in the mountains of West Virginia at the Green Bank Observatory. The Green Bank telescope is the largest movable structure anywhere on land. So it's this gigantic hunk of metal that we use to study very, very distant astronomical objects. And as she said, if you do have any questions, feel free to ask them and I will pepper them throughout the talk. Just as sort of a background of the talk, we're going to start a little bit chatting about what radio astronomy is, how it's different than optical or infrared astronomy. Then we'll get a sense for our place in the universe, zooming out from Asheville the whole way to the size of the observable universe. And then we'll talk a little bit about how scientists are currently mapping out the structure and the chemistry of our home galaxy, the Milky Way. So let me go ahead and share my slides here. Great. On this first slide, we have an example cartoon of what the Milky Way galaxy could look like. And anytime you see this red star throughout the talk, it's going to be used to indicate where we are, red star, red circle, just giving you a sense for where our place is in this schematic. So a little bit about my background. I am from Ford City, Pennsylvania, which is about 45 minutes northeast of Pittsburgh, sort of a bit further north in the Appalachians than Asheville is. I'm an astronomer. I went to Westminster College for my undergraduate, where I studied physics. And then I went to West Virginia University for my graduate degrees, where again, I got a master's and a PhD in physics. A lot of astronomers do have physics degrees. Astronomy is sort of a subset of, or a branch of the physical sciences, branch of physics. So I would say about half of the astronomers you might meet, their degree is not actually astronomy, it's in physics. And then sort of as a little bit of a fun background on me, I've worked for a very long time in catering, and sort of a current passion project is that my siblings and I are trying to revive a very old building back in our hometown, where one day I hope to also have a planetarium in the attic. So there's a little bit of background on me. Feel free to ask any more that you would like. Just as a reminder about that red star schematic, you are right there. We'll burst now into our introduction to radio astronomy. So whenever you think about astronomy, really what you're talking about is anything that you're studying that is outside of the Earth. So if you are studying things high in the Earth's atmosphere, the whole way to the imprint of the first things we can see at the start of the universe, you are talking about astronomy. It's everything that is outside of the Earth. Radio astronomy in particular looks at a wavelength range that is much longer than optical wavelengths. So your eyes are great at seeing things with a wavelength from, let's say, 500 to 800 nanometers. That means the wavelength of light goes from 500 nanometers wide to 800 or so nanometers wide. For radio wavelengths, you might be looking at things that are about this thickness of 2 sheets of paper, the whole way to many meters or even kilometers long. So you can be looking at things basically the size of 2 sheets of paper up to the size of buildings. So when I say radio astronomy, really that's just a branch of astronomy that is limited to those long wavelength observations. An advantage of radio astronomy and of optical astronomy is that most radio and optical light are able to pass through the Earth's atmosphere. If we look at other branches of astronomy, for instance, infrared, ultraviolet, X-ray, and gamma ray, our own atmosphere blocks that light from coming through. So you have to have telescopes out in space if you want to do infrared, ultraviolet, X-ray, or gamma ray astronomy, whereas you can do optical or visible and radio astronomy from the ground. Stepping through what some telescopes might look like I said, you can use telescopes that you look through with your own eyes to look at optical sources of astronomical objects. If we want to go to infrared astronomy, we really have to put something up in space. And so this is a picture of NASA's Hubble Space Telescope, which has been around since the early 90s. We do have a new telescope that will be sort of the heir apparent to Hubble that will hopefully be launched here in the next few years. That's called the James Webb Space Telescope. And here's a telescope that is very near and dear to my heart. This is actually the Green Bank Telescope in Green Bank, West Virginia. So I mentioned that optical and radio, you can use instruments that are on the ground. And so the Green Bank Telescope is firmly rooted to the ground. For some more background on the GBT, like I said, this is nestled in the West Virginia mountains, and that's by design, right? Radio telescopes can be extremely sensitive, not only to natural emission that we're looking at from sources from the sky, but to man-made radio emission. So what does man-made radio emission look like? It looks like your cell phones or microwaves or Wi-Fi, even garage door openers or remote control cars, right? The way that your cell phone communicates with a cell phone tower is through radio emission with similar wavelengths to the objects that we are looking at in space. And you can imagine being so close to the telescope, those sources of emission would just wipe out any objects that we are looking for out in space. So the GBT is huge. It has a collecting area of about 2 football fields, whether you want to talk about American football or soccer. And it is the largest steerable structure anywhere on land. So it's about 485 feet from the base up to the top. And it's not the largest structure anywhere on land, but it is the largest one that can actually steer around and point. So there are some radio telescopes that are slightly larger, like Arecibo, for instance, which is in Puerto Rico, or there's an even larger one called FAST that is being constructed in China, but those are fixed to the ground. They can't move around. The GBT has the ability to point anywhere you want in the sky as long as it's above the horizon. So let's see, we have a few chats that are coming in here. Is there a telescope that can capture all of the electromagnetic waves? In theory, you probably could build one, but you would have to have a variety of sensors in that telescope that are each sensitive to a different wavelength regime. So I'm going to go back to an example I talked about, using your eyes to look at radio or to look at optical emission. The reason that you're able to see optical emission with your eyes is that the cells that that are in the back of your eyes are tuned specifically to that wavelength range. If you were going to be able to see radio light, your eyes would have to scale with the wavelengths of light. So you might have 2 eyes that, instead of being an inch across, are 3 feet across. So telescopes are the same way. The apparatuses that they have to look at light from different sources have to scale with the wavelength. Otherwise, you can't detect it. So to answer that question again, is there a telescope that can capture all electromagnetic waves? There is not currently. You could potentially build one, but it would be very, very hard. A next one is, how does using Wi-Fi at work not interfere with the telescope? So in Green Bank, all of our internet connections are corded. We have no Wi-Fi in our offices. So everything comes from an Ethernet cable that we plug into our computer. And everyone who lives around the site, there are about 100 people who work at Green Bank and who live in the surrounding areas. If you live on site, you are required not to have Wi-Fi. So I wired my house with probably about 1,000 feet of Ethernet cable when I moved in. So I can still have internet anywhere in my house, but it's not as convenient as Wi-Fi. And a last question before we move off this slide is, will the James Webb Telescope be more focused on looking at the origin of galaxy development post-Big Bang, looking for other planets in the habitable zone, or looking throughout our own galaxy? I think that the James Webb Telescope will be touching on points of all of these, actually. It's a pretty versatile instrument and is considered part of what NASA calls their Great Observatories projects. So Hubble was a great observatory. It's meant to be a very, very impactful instrument across the entire world and be around for several decades. And I believe that James Webb is tackling some of each of these. One background on NASA versus the National Science Foundation. So NASA funds any telescope that is out in space. So they control James Webb, they control Hubble, and then the National Science Foundation funds any observatories that are on the ground. So the Green Bank Telescope is funded by the National Science Foundation. The telescopes on Mauna Kea and Hawaii that are run by the United States are run by the National Science Foundation. So that's the difference. NASA does stuff in space, National Science Foundation does stuff on the ground. Now, we talked a little bit about radio interference and how things like cell phones and Wi-Fi can interfere with that. To protect Green Bank, there's actually something called the National Radio Quiet Zone. So this was set up in the 1950s by the US government and is 13,000 square miles where we can limit radio broadcasts. So you can see here's an outline on the left of a portion of West Virginia, and then we have Virginia, a portion of it on the right. This is a gigantic area. Now, just because you live within this area does not mean that you can't have any radio broadcasts or you can't have a cell phone or Wi-Fi. But things start to become more constrictive or more restrictive as you move closer to these sites. So the Green Bank is here on the left where it says National Radio Astronomy Observatory. And then there was a naval station towards the right, that other red dot. This radio quiet zone was set up to sort of cover the center portion between those two. This National Radio Quiet Zone doesn't prohibit individuals from having radio transmitters, but it does prohibit companies. So anywhere in this zone, if you are a cell phone company and you want to put up a cell phone tower, you have to put an application into the National Radio Quiet Zone office, and we will go through tests to make sure that it won't actually interfere with the observations at Green Bank. Now, if you are on sort of the far end of the National Radio Quiet Zone towards Buchanan, for instance, you're not going to have a problem. But if you want to put something within, say, 20 miles of Green Bank, you're probably going to cause problems for the observatory. And so what that means in general is that there is no cell service right around Green Bank. This site was also picked specifically because it is very rural. In the 1950s, whenever they set out to find a place for the Green Bank Observatory, they were looking at places where the population was low and didn't look like it would be growing anytime soon, and making sure that we were significantly far away from any kind of large population centers. And so because of that, it's already a rural area, and rural areas, as I'm sure you might be familiar with, can sometimes have very limited cell broadcasts anyways. So the rural nature of Green Bank sort of helps us in that regard. Now that we've talked a little bit about radio astronomy and Green Bank, it looks like there is one more question that comes through. So Kayla asks, when you say interference, do you mean that connection for the telescope becomes poor or less useful with radio or Wi-Fi use, or do you just collect data you don't want? We basically just collect data that we don't want. And so if you have a cell phone that is beside the GBT, the Green Bank telescope, the signals coming from that cell phone are going to be so strong that we will collect them with the GBT, and it will basically wash out any kind of astronomy signal that we're looking for. Some typical signals that we could see with the Green Bank telescope would be 10 to the minus 26 watts. So if you think of a normal light bulb that might be 60 watts, and then you add 26 zeros before that, so 0.000000, blah, 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 60 watts. That's sort of the strength of signal that we're looking for. So they're very, very, very tiny, and any sort of man-made signal is going to completely wash out that data. So I hope that answers your question. Next, we're going to sort of zoom out from Asheville and look at our place in the universe. So let's take a quick trip to the edge of our universe. Here's North Carolina. I'm not currently in North Carolina, but virtually I am. And as we zoom out, the next bigger sort of astronomical structure is the Earth. So we are on the Earth, and here's again that red circle to give you your bearings. If we zoom out even further, well, Earth is the third planet from the sun. You can see all of these other guys lined up after the sun. This is not to scale at all. Jupiter, Mars, Venus, and Mercury are all much further from the Earth. But as we zoom out from the sun, we might start to think about things that look like the Milky Way. And so this is an artist's conception of the Milky Way with the position of the sun shown here. The sun is about halfway out from the center of our galaxy out to the edge in what's called the Orion Spur. So you can see here we have a couple spiral arms that look like they're coming off towards the center of our galaxy. But a thing to point out is that even though this looks beautiful, it is not an image of our galaxy. It's not a picture, right? If we were going to get this picture, we would have to go from the sun and fly way above the galaxy to take a picture down. And if we were going to do that, we would have to travel something like 100,000 light years, which means it would take light 100,000 years to get up there and then 100,000 years to come back. But our current spaceships can't go anywhere close to the speed of light. So in practice, if we were going to take this picture, it would take us millions of years to get up there, snap the picture, and millions of years to come back down. So anytime we make a map of the galaxy, we have to do it from the Earth. And we'll talk a little bit more about that in the next section. Zooming out from the galaxy even more, we have what's called the local group. And so this is a group of other galaxies that are hanging out with the Milky Way. And most of these are what we call dwarf galaxies. So they're not these big, beautiful spiral galaxies like the Milky Way. They're just sort of big clumps of stars that are still galaxies and still forming new stars, but they're not nearly as massive as the Milky Way. And so over here you can see Andromeda, which is part of our local group, and the Triangulum galaxy, again, which is part of our local group. And all of these galaxies likely formed out of the same giant clump of gas billions of years ago that condensed into these smaller galaxies. That's not as big as it goes, though. This is just our local group. And our local group is part of what we call a supercluster. So this is the Laniakea supercluster, and our local group is shown in this red circle here. You can see we're not even really a major part of our local group, we think. There are all of these other local groups, like the Virgo cluster, Centaurus cluster, the Leo groups, the Hydra cluster, that all have lots and lots of galaxies in them themselves. So you might think that this supercluster is as big as we get. Let's see, there is another chat in here. How do we collect data so far away? Well, it takes really, really sensitive telescopes. And most of these would be using likely telescopes in space if you're looking for the optical light. Optical light tends to be more intense than radio light, but it also has a problem where it doesn't like to travel as far, because optical light can be absorbed by gas and dust in between you and those objects, and radio light isn't really affected by gas and dust. We'll also chat about that a little bit in the next section, where we talk about mapping the Milky Way. But it just takes a lot of time where you're looking at very, very bright objects that are far away, and the signals that you get are going to be just maybe tiny little bumps on a plot that don't look like much for you if you're looking at your computer screen. But if you take into account how far away they are, you're actually looking at these giant structures very, very far away. So moving out from our Laniakea group, we have the observable universe. So we think that the universe was created about 13.4 billion years ago. It's actually about 95 billion light years wide. So you can say, okay, if it was created about 14 billion years ago, how is it 90 plus billion light years wide? Well, it's because the universe is expanding. It's still expanding. And so ever since it was created in what we think was sort of a big bang, where pure energy turned into elements, and that turned into other gas, and that turned into stars, and that turned into planets and humans and plants and things like that, it has been expanding away from that singularity. And so we actually will never be able to see all of the universe. You might hear people talk about the observable universe. That's the portion of the universe where the light has had time to get to the Earth. So there is also this unobservable universe that is outside of the observable universe. So yeah, if you want to think about sort of your place in the world and how small we are compared to what all is out there, I think that can be sort of hard to think about, but it's also amazingly cool to think about this giant mammoth universe creating something like you or like me. So you can think about it in the way that makes you feel small and insignificant, or you can think about the universe conspiring to create something awesome like you. So that's sort of the motivational portion of this talk. Let's see, there's another chat coming in. How do artists come up with the visuals based on the data? Is it something that is produced from running a sort of code with data to produce a graph of sorts? There are different ways. So something like this that you can see probably took some information about what we think is out there, and that we have clusters of really dense numbers of galaxies, and then portions that are pretty empty. And then an artist says, okay, I have data from the scientists. Let me go and create what my interpretation of that data is. And so this is an artist conception. But you can also do things that just look at the data that you have and only plot that. If you want a really beautiful or complete looking picture, you have to fill in some of the gaps based on assumptions or inferences. And that's whenever it really becomes art and not just science. So this is art, but use science to inform what it actually looks like. So here's a reminder of where our journey just took us, from Asheville out to the size of the observable universe. And next, we're going to talk specifically about our galactic home, the Milky Way, who's dancing away in the center. If we start to think about how people first started to do this, the first character to come on the stage really was William Herschel. So up until the time of Herschel, people thought that anything that they saw out there in sky, even if they were looking at things that looked like spiral galaxies, they thought that they were parts of our own galaxy. And turns out that that's not the case. We just saw that there are bunches and bunches of other galaxies out there that are discrete structures outside of the Milky Way. And it was Herschel who started to look at specifically stars and tried to plot how far away he thought each of the stars that he could see were. Now, the way that he did this was he looked at a portion of the sky and said, okay, I can count 30 stars in this region. And so he thought if there were more stars in that direction, then the galaxy probably went further in that direction. If he looked in a certain direction and only counted a couple stars, then maybe the galaxy doesn't go as far in that direction. And so that's how he produced this first map of the Milky Way. And you can see in some directions, let's see, I think I have the portion of the sun here. So here's where he thought the sun was. You can see in this direction, it looks like galaxy goes out in a really long way. Whereas if you look in this direction, maybe the galaxy sort of stops right there. So what he was actually seeing were dust lanes. So I mentioned before that optical light doesn't travel very well through interstellar gas and dust. And so in this portion of the sky, it turns out that there is a lane of interstellar dust that was just blocking starlight from coming through. So there are actually stars behind that dust, but he just couldn't see it. And because of that, you get sort of a weird looking map of the Milky Way if you use only optical light. To me, this sort of looks like a strange duck head, where the sun is maybe offset from where the eye should be, but here's the bill of the duck. And so to look at what that actually looks like, we have an image of the same portion of the sky taken at different wavelengths. So shorter is closer to the optical range, longer wavelength, like 2.16, is closer to radio. This is all actually in the infrared range, but it demonstrates the same thing. So you can see at shorter wavelengths, light can't pass through, but as you move to longer and longer wavelengths of light, you can basically see right through that gas cloud. So I do see a question coming in here about the size of the observable universe. Let me quickly go through and address that as you sort of process what I've just talked about, optical light. So I've heard the number 93 billion light years is across as the size of our universe. Does that include the calculation for the unobserved, or does that stop at the observable? That, I believe, stops at the observable edge of the universe. So that's sort of a lower limit for how wide the universe is. And if we would include the unobservable universe, it could be even bigger, right? So good questions all. All right, so if optical light is blocked by interstellar clouds, what are we going to do? Well, for me, I'm going to move towards the radio end of things. And I've mentioned a couple times already that every map of the Milky Way that you've seen is an artist's conception. Here are a couple of those. So here's Herschel's map of the galaxy, the duck bill. Here's the cartoon that we looked at earlier that is beautiful and takes some science into account, but isn't really scientific truth. And here's an example of spiral galaxies that you can create through computer simulations, again, taking into account some science, but then making inferences or guesses about how the structure should actually look. And so this is some modeling code that I've worked on that we'll look at a little bit more towards the end. So why do we even want to know what all is out there in our home galaxy? You can think about it to some extent as a parallel of mapping out land hundreds of years ago, just partly to know what all was out there. But here on the Earth, that meant that maybe you could know where there is water and where you could go and drink fresh water. So there are real tangible reasons to mapping out the land on the Earth, whereas out in space, all of these objects are so far from us that we are never, in the foreseeable future at least, going to visit the far side of our own galaxy. So why do we care about mapping it out? Well, to some extent, it gives us new knowledge about how the universe was created, where we're going, and just more information about our own galaxy and how it will evolve over the next 1,000 million billion years. So if we do map out our galaxy, we'll get a better understanding of its total brightness, the total luminosity of it, how individual objects in the galaxy contribute to that luminosity. So I say here the H2 region luminosity function. We'll talk about H2 regions next. How quickly it's forming stars. Does it form stars very rapidly? Do they pop up pretty much all over the place all the time, or does it take a long time to form a star? How efficient we are at forming those stars, so going from gas into stars. And then a little bit about structural details. So is the sun in a normal place in the galaxy? Is it in one of these spiral arms? And what does the far side of the galaxy even look like? So through mapping out the galaxy, we can go from something like this that is actual data using one set of tracers that we'll talk about here in a minute, to something like this that we sort of think about whenever we think about what the Milky Way structure actually looks like. So there's a question here: is there any viability to sending out multiple telescopes into calculated orbits to create a sort of information relay to circumvent dust and other light obstructions? So the first thing that pops to mind for me on that front is something called interferometry. So to answer your question about circumventing dust, all of these dust structures are going to be so large that you would have to send telescopes light years or even hundreds of light years away to look around them. And that's really just not feasible for us. But you can use radio telescopes, for instance, and a technique called interferometry, where you set up telescopes in different portions and look at the same object, and then you correlate the signals that come back to those two telescopes to get better resolution, more information about those objects. So something like the Very Large Array in New Mexico is an interferometer. Now those are all on the Earth, right? But we have sent out other telescopes to space to do the same thing with telescopes further apart. So Russia had a telescope called Spectre-R, or Radio Astron, that was a partner with Green Bank, actually, to do this sort of interferometry from space. So that's sort of what comes to mind with your question. If I didn't fully answer it, let me know. Now, thinking about everything that we've talked about so far, to map the galaxy, we're going to need, first, extremely sensitive telescopes. You can do local mapping just in your backyard with an optical telescope, but you'd run into some of the same problems that Herschel did with his first map of the galaxy, where you can't see through the gas and dust that's nearby and blocking that optical light. You also need objects that are bright enough to see across the entire Milky Way. And so we could think about the brightest objects are going to be the most massive stars and the regions around them. You're not going to necessarily be able to see very faint stars across the entire Milky Way. And if we want to map, we need a way to determine the distance to those objects. So enter again the Green Bank telescope. This is the same slide that you saw before. We could use other radio telescopes for this problem too. I already mentioned the Very Large Array and Arecibo and the FAST telescope, but we have similar telescopes in the Southern Hemisphere as well. Astronomy observatories really have to be all over the world if we're going to map out all of space, because you can only see a portion of the night sky from the Northern Hemisphere. There are constellations and galaxies that we will never be able to see from the Northern Hemisphere and from Northern telescopes. So if we want a full picture, we have to have Southern counterparts. And many of those telescopes are in Chile and Australia and South Africa, as well as a few actually on Antarctica. And those sites were all chosen in part because they have clear skies. For radio observatories, there are also large portions of those places that are uninhabited. You can think of the deserts of South Africa, the Karoo region. Western Australia is pretty sparsely populated. And then the mountains of Chile are high and with very little population density. So we select those sites for similar reasons as Green Bank was selected as the site for the Green Bank telescope. Now I mentioned H2 regions and that we needed an object that you could see across the entire sky. And so for me, this is the object that we use to trace out the structure of the Milky Way. It's HII, which is pronounced H2. The II is for the ionization state of hydrogen actually. So H1 is unionized hydrogen. It's a proton with an electron orbiting around it. Hydrogen only has one electron. So if you pop that off, then you just have a bare proton and you can't ionize it anymore. So this just bare proton is H2. If you had other elements like helium, you could go even higher because they have more electrons that you can pop off. So you can have helium 3 and 4, etc. Now, H2, or ionized hydrogen, surrounds really, really high mass stars. Whenever you have a very bright, very massive star, it emits intense radiation that's able to strip all of the electrons off of those hydrogen atoms. And what you get is a very bright glowing cloud that can be seen across the entire galaxy from the mid-infrared wavelength regime through radio. So these are very, very bright objects. To think more about this ionization, if you were to flip on the switch for a fluorescent bulb, you're doing really the same type of things where you're passing energy into this chamber full of gas and you're using that energy to take the electrons away from the atoms. And then the electrons go back and combine with the atoms and emit light when they do that. So it's a very similar process. These H2 regions we call zero-age objects compared to the Milky Way. Now, the reason we say that is because high mass stars sort of live fast and die relatively young compared to lower mass stars. They burn through their energy or use their energy and matter much more quickly than lower mass stars do. And so they only live for millions of years. Now, on a human time scale, millions of years is a very long time. But if you compare to stars like the sun or of structures like galaxies, a million years is that. It's just a figurative galactic finger snap, right? And so when we say that these are zero-age objects compared to the Milky Way, we're saying really that they trace the state of the galaxy as it is right now in this current epoch. Whereas older, more low mass stars are able to trace the history of the galaxy. So the sun is going to live for about 10 billion years total, whereas the stars in this H2 region are only 10 million years, right? So they have lifetimes that are 1,000th the lifetime of the sun. And so we're able to really trace out the current state of the Milky Way galaxy. Here's a question about, again, about the Green Bank telescope. Does the Green Bank telescope have an advantage of being in the mountains? It does. So the mountains are sort of an extra shield against radio interference. There's sort of a natural bowl of mountains around Green Bank that are 3 miles in diameter, almost in every direction. Now, it's not a perfect bowl, but what that does is it keeps stray interference from over the mountains from coming inside. In some directions, if you go over the mountains, then you can get cell phone service. But as soon as you cross over the peak, it disappears. So that's sort of another natural barrier for having Green Bank where it is. I have this expanding bubble around the H2 region. They do increase in size as the stars evolve. And that's a way you can trace the age of an H2 region, basically based on its size. Now, through some of this work, we've compiled a bunch of known H2 regions across the galaxy. So we have 2,000 regions that we know are H2 regions, and about 6,000 that look to be H2 regions, but we haven't confirmed yet. And we do all of these through infrared measurements with the WISE telescope that was launched by NASA in 2009. And it looks like all of these H2 regions have the same shape in the infrared, where they have a 22 micron core, and that's shown by red in this diagram down here. And then they have more diffuse 12 micron emission surrounding them, and that's shown by green in this diagram. So the core is really tracing the high mass stars that are at the center of the H2 regions. And this diffuse 12 micron envelope is tracing what we call PAHs, or polycyclic aromatic hydrocarbons. These are rings of hydrocarbons, so carbon and hydrogen, and occasionally some other elements that are basically the same thing as the sooty char you get on grilled meat. If you go out and grill a steak, you're going to get some char marks. And a major component of that char is going to be these polycyclic aromatic hydrocarbons, which you might have heard before that charred meat is slightly carcinogenic. These PAHs out in space are also slightly carcinogenic. They're the same component. And so it's kind of cool to think about gas that you can see out in space being the same type of stuff that you can create here on Earth in your backyard. And so after we determine all of these candidates in the infrared, we confirm with radio observations. So here are some of those beautiful candidates. You can see maybe they look a little bit ominous, like Eye of Sauron-esque. But you can see the 12 micron core and then the more diffuse envelope of PAHs. Let's see, there's another question that came in. Are the telescopes that you use connected to a spectrometer that just track light absorbance? Or do you use some sort of mass spectrometer to trace minerals? Telescopes like the Green Bank telescope are pretty much a spectrometer. So our major back-end component is a spectrometer. And we just upgraded ours about 6 years ago to be able to look at wider bandwidths and be more sensitive with the same instruments that we have on the front of the telescope. So to some extent, we are just using a spectrometer, like a mass spectrometer that you would use in a lab. There's another question about H2 regions. Do H2 regions only collect around high mass stars, or could they potentially collect around black holes? You could have some of the same ionization of hydrogen around other massive objects. Anywhere where you have lots of energy that can go into pumping the electrons off of the hydrogen, you can create that ionized hydrogen. So you should see some where there are stars sort of spiraling into black holes. But we wouldn't necessarily call that an H2 region, even though it is comprised of H2, just because the class of H2 regions is defined to be sort of objects around high mass stars. So yeah, it would be some of the same emission. Here is an example of a spectrum we can get. So this is right in line with the question about a spectrometer. And you can see on the y-axis, we have intensity. One of our intensity units is antenna temperature. And on the x-axis, we have velocity or frequency. You can convert between the two. And here's an example of a detection of ionized hydrogen. So we know about where these lines should be based on the rest frequencies of the molecules. And then we can go and look in the spectrum at those frequencies to see, okay, do we see a line there? And usually we can orient ourselves by other lines that are in the vicinity to make sure that we're not just looking at a source of interference, but we're actually seeing our astronomical object. And so through this work, through looking at infrared images of these red blobs surrounded by green blobs, or H2 regions, turned out that 95% of the sources that we observed, that we had looked at in the infrared, were confirmed to be actual H2 regions. So this was a good selection criterion for our survey. And we've more than doubled the number of known H2 regions across the Milky Way in both the northern and the southern hemisphere. So one question you might have is, okay, we have a line detection. How do we determine a distance to those objects? And the way we do that is by having a model for how we think the galaxy moves. So in general, we think that the galaxy is a disk and it rotates. So you can put down, based on the position of the sun, what velocity you would expect on that rotating disk of the galaxy in any direction. Now, from your line, you can get the velocity of the source in the same way that you could, in principle, get the velocity of an ambulance coming towards you, right? As an ambulance is coming towards you, the frequency of sound that you hear is higher than if the ambulance were just sitting still. As the ambulance passes you and moves away, that frequency goes lower. So I'll do a demonstration. It might go from wee 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 to wee 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 as the ambulance passes by you. And so that's called a Doppler shift. And we can use that same principle to get the velocity of these objects in space, whether they're moving towards us or away from us. So using that velocity that we can obtain and this model for the rotation of the galaxy, we can determine a distance to those objects. So let's see. Let's say that I'm looking at a position in the sky that has a longitude of 50 degrees. That might be, let's see, sort of in this direction. And I measure a source velocity of minus 80 kilometers per second. That would be sort of 50 degrees. And let's see, I would go to where I see a source velocity of 80 kilometers per second. That would be on this line right there. And so I would say from that model and the velocity I detect that my source is way out there in the outer region of the galaxy. So there is another chat here. Is there a coding software that is most commonly used in astronomy for this type of work and for others? And what advice would you give to educators trying to get kids excited about these complex concepts? So the vast majority of astronomers use a language called Python for their work. And there's a package specifically called AstroPy, which is developed by astronomers and scientists around the world, that is all free and open source. So anyone can go in and try to get their hands dirty with astronomy software using Python. Now, Green Bank currently uses a different, an older system that's based on, it's called IDL, which can do many of the same things as what we do in Python, that it's sort of not as actively developed as Python currently is. So we're having some discussions about whether we should move to this newer language. And most astronomers, myself included, use Python pretty frequently. What advice would I give to educators trying to get kids excited about these complex concepts? I think that hands-on instruction is awesome, and you might think that it can be hard to get hands-on experience with astronomy, but really it starts with going outside and looking up at the stars. And in that sense, I think astronomy is very accessible to most people. Even if you live in a city where there's lots of light pollution, you can start with the moon and maybe some of the brighter planets. And then many observatories, Green Bank included, have programs designed towards engaging students from elementary school up through college and grad school level. So we have a telescope that is specifically for teaching that is still very large. It's 20 meters in diameter. So what is that in feet? I use feet and everything else, but meters whenever I'm talking about telescopes. So that's sort of 60 feet across. That is specifically for teaching programs. So I would encourage you to go on the Green Bank Observatory website, greenbankobservatory.org, and look at what some of those programs are. Typically, we have lots of in-person summer programs. Those have been sort of postponed this summer, but we have virtual experiences that we're continuing throughout this summer too. Now, I mentioned this H2 region discovery survey and that we can only see part of the sky from the north. All of the shaded region is this part of the sky that we can see from the north here. And I mentioned that we've detected lots and lots of these high mass star forming regions in the northern hemisphere. But we have some projects to try to go beyond the portion of the sky that we can see easily with the Green Bank telescope and try to get a more complete map of the galaxy. So one of those is what we call the Southern H2 Region Discovery Survey. And we use a telescope in the Southern Hemisphere in Australia called the ATCA, which is in Narrabri, Australia, a bit north of Sydney, to try to detect lots and lots of these high mass star formation regions in the part of the sky that we can't see with the Green Bank telescope. And so that's shown here on this face-on map of the galaxy in yellow. I have a project that I've worked on throughout my PhD and I'm currently working on with a student named Alex, who we are looking at the very far outer regions of the galaxy in what's called the Outer Scutum-Centaurus Arm. These sources seem to be the most distant objects from the sun that are still high mass star forming regions in the galaxy. And then we have another project that is looking at some of the faintest H2 regions in the galaxy, sort of out in the opposite end of things, out away from the galactic center. The galactic center is there and the sun is at this red star. These radio quiet or radio faint objects are out there. Here's an example of the Southern H2 Region Discovery Survey. We've actually detected about 500 new H2 regions in this region. And so we've also doubled the census of high mass star formation way out there in the portion of the sky that we cannot see from Green Bank. So in the last couple minutes, I'll talk about some modeling work that uses much of this data that we've actually detected and looks toward creating those beautiful pictures of the spiral Milky Way. So here's some work where we incorporated known Milky Way structures. So we populate in this code that is all built in Python also, 4 main spiral arms. And let's see, I label those here. So you can see here's an example spiral arm, here's an example spiral arm, and then we have 2 over here as well. We also think that there's this bar of star formation towards the center of the galaxy, and that's shown by this line here. It seems to be pretty much a linear structure. And then we have these arms that are much closer into the center of the galaxy called the 3 kiloparsec arms. There's one on this side, and there's also one on this side of the galaxy. So those are what we think are sort of the main features of the galaxy whenever you look at it from above. But we also have many stars that are not produced in these spiral arms. So we haven't talked much about how we form stars, but the spiral arms are spiral arms because they're an overdensity of gas, and that overdensity of gas forms new stars. So you can also have some random clumps of gas that are not in a spiral arm that is still producing stars. And so we have some of these stars that are not perfectly in spiral arms. Here is some simulated versus observed data, and the size scale is not perfect here, but it gives you a sense for sitting inside of on the Earth basically and looking out at the galaxy, what these H2 regions could look like. So this data is not manipulated in any way by a model, it's just what we see. And so on the bottom are some observed H2 regions, and you can see towards the center of the galaxy, which would be along this central line here, we have more H2 regions, and as you move out away from the center of the galaxy, those sort of drop off. And I think one final view, you can see, you might think that it can be quite a stretch to go from this observed view of what H2 regions look like in the Milky Way to this beautiful, in my opinion, spiral image of the galaxy. But we have been building up this information for what we think the Milky Way looks like for many, many years. And so this step between here and this simulated model is to some extent science, and it is to some extent making educated guesses about what the Milky Way should actually look like. And then if we were to overlay this with pretty colors and make it more appealing, then the art starts to come in. And so many of these visuals are a mix, as I've said, of science, inferences, and art. And so that is all that I have for this story, but I'm very happy to answer any other questions you have. And I hope that I've answered much of what you've thought about throughout the talk. I'd also, again, point you to the greenbankobservatory.org website for any other information you might have about some of our outreach and engagement programs. So thank you very much.
Thank you, Will, so much for joining us today. And I would definitely highly encourage everyone watching to check out the Green Bank website. They have amazing resources for educators. And I believe right now you guys are doing virtual tours of the telescope site. So a lot of really cool stuff. A lot of this stuff is really, out of this world. So if you guys have any other questions, definitely send them to myself, the Asheville Museum of Science page on Facebook, or you can reach us through any other of our website social media sites. Will, thank you so much for your time. We really appreciate it. And I hope to see everyone back next week.
Thank you very much. It's been fun.